So I'm going to talk about what Steve said, localization and particle filters. This is really not, it doesn't involve much work that I've done. It's more trying to keep pace with a subject that's evolving rapidly. We have people in the audience who've done more work on this than I have, and I will defer questions to them as necessary. So I am going to give a bit of a review, and I want to kind of start from the beginning. So just the basic notation, the state is going to be the boldface X. The observations I want to simulate are boldfaced Y. And I know some relation between the state and the observations that has noise in it. So I can't know the state precisely. This is because both my observations and the forecasts I'm going to use in the data simulation are going to have error. So I'm going to take the point of view that the most I can know about the state is its probability distribution. So the PDF, P of X given Y. So I really want to know this probability distribution conditioned on the observations. I'd like to approximate this. I'd like to estimate it without making assumptions like that it's Gaussian. I'd like to be able to use observations that have arbitrarily nonlinear relations to the state, observation areas that are non-Gaussian. Yeah, so this is kind of my goal here. Just to back up a little bit, because this is not actually in the talk, but the stated goal is really computationally intractable beyond a few dimensions. So actually constructing a high-dimensional PDF or estimating it in a discrete form is incredibly difficult because it's a function of many, many variables. So if I'm doing NWP and I have 1 million variables, P of X given Y is a function of 1 million variables, and I want to discretize that, and it's going to be an astronomical number of floating point numbers that I have to store. So that's going to motivate using ensemble methods for this instead of trying to estimate the PDF directly. Okay, so the other thing I'm going to use is Bayes' rule. Everybody knows this, but I just want to write it down, and I want to say, keep an eye on the observation likelihood that's red. Okay, so things that are related to it, I'm going to try and make them red in the future. Okay, so particle filters. Basically, I'm going to drift back and forth in terminology between two sets of jargon. Particles are the same as ensemble members, and samples are the same as ensembles. So I will use those terms interchangeably. The notation for just some common constants, the dimensions I denote by capital N's with little subscripts that tell me what is the dimension of. So n sub y is the dimension of the observation vector, n sub e is the ensemble size, and n sub x is the dimension of the state. And then the particle filtering literature uses this specific notation for ensemble members and times. So the superscripts denote the ensemble member. This is the ith ensemble member, or the ith particle. And the subscripts are times. This is the kth time. One final thing is if I've got a subscript that's got a colon in it, that just indicates that I'm concatenating all the vectors associated with those subscripts together into one long vector. So it lets me talk about things over multiple times at once. Okay, so what is a particle filter? Well, we've heard a lot of talks about these already, but I just want to kind of, like I say, go back up a little bit. So that is, this is a sequential Monte Carlo algorithm to sample from this thing that we want to know about, the conditional distribution. So it's not going to make any assumptions about the form of this conditional distribution. So it's non-parametric in the statistical lingo. There's a big literature. You can blame the financial crash on particle filters partly, okay? So there's lots of use of particle filters in mathematical finance, and there's been a lot of interest in the geophysical literature as well. Okay, so how do these things work? So basically the generic form of, it's a sequential algorithm. So what I want to do is I have an ensemble at some time k minus 1. I get new observations at time k, and I'm going to generate new particles at the new time through some fashion. Okay, I can basically draw them from whatever probability distribution I want, and I can use the past values of the particle, and I can use the observations as I please. There's a formula for computing weights that goes with each of these new particles. I'll tell you sort of the simplest case in a second, but there's a general formula depending on however I decide to generate the particles. I can compute weights that will consistently, as I take many, many particles, give me back the Bayesian update. Okay, so now at this point I've got a bunch of ensemble members and I've got weights on each one. So the next step in the sort of generic algorithm is to resample from that empirical distribution. So I can think of, I've got n ensemble members. I can think of those as being basically delta functions, point masses at the location of each member. They have weights associated with them, and then I want to sample according to those weights from the ensemble members. And I get a new set of members that are equally weighted. I'll replicate some of the members that have high weights, and I will ignore some of the ones that have low weights. And then I just repeat this over and over again. Okay, so it's really elegant in that you just use the model, and you have to calculate weights, and that's about all you're doing. So this is, let's take the simplest case, okay? So I'm going to begin, like I say, with members drawn from this conditional distribution at the previous time. And the simplest thing I can do is generate the new members just by making an ensemble forecast. So I'm going to evolve. I'm going to take the old member. I'm going to evolve to the new time using the dynamics that I have in the model. And then the right way to compute is just this. It's going to be proportional to the likelihood of the new observations given this new member. Okay. So then I'm going to sample, and this is kind of the schematic picture, the classic one from one of Arnaud Doucet's introductory articles. Basically, you come in with a bunch of equally weighted particles. Just think about a one-dimensional example. You've got some likelihood function in black that's going to give you weights on the particles according to whether the likelihood is big or small at that given that particle. I resample, so I'm going to replicate the particles with big weights multiple times, and some of the particles that didn't have much weight, I'm not going to keep at all. And I just repeat that over and over again. Okay, so where does this weight come from? It's really easy to see in this simple case. If I've got Bayes' rule that looks like this, and I say that this prior distribution is just given by a sum of delta functions. So this is the empirical distribution if I have a sample from that thing. And I plug this representation of the prior distribution back into Bayes' rule. Then what I get is just a sum over these delta functions. And the likelihood, now I just have to evaluate at the locations of the centers of each of those delta functions. Okay, so I just get these weights. So at this likelihood is evaluated at each of the new members. Okay. So the weight that I'm going to assign to each of these new members is just proportional to their likelihood, the likelihood of the observations given that member. So the key issue here is that these weights you tend to get one weight that is close to 1, and all the rest are teeny. Okay. So let me just show you how this works in a very simple test problem. I'm going to take the prior to be just a normal zero identity, so everybody's IID with a unit variance. The observations, I'm going to observe each element of the state vector with noise that is, again, IID normal 0, 1. And I'm just going to do the update. Okay? And what I ask is, how big an ensemble do I need to, let's say, not do worse than the observations? So some very minimal test, okay? So this shows that required ensemble size as a function of the dimension of this underlying problem, nx and ny, okay? And this is a log plot. So basically the required ensemble size to avoid this degeneracy where one weight is going to 1 grows exponentially as the dimension of this simple problem, okay? So yeah, it just gets to be that you need very, very large ensembles very quickly. Okay. So there are asymptotic results that tell you how this dependency happens. If you define a quantity tau squared that's the variance of the log of these unnormalized weights, then you can show that as this tau squared gets big, then the ensemble size required to keep the maximum weight from going to 1 grows as e to the tau squared, basically. Okay, so there are some details on this that I can go into in the discussion, but basically this means that for a wide class of problems, particle filters are going to be hard, okay? And I'm going to skip this part because I'm running behind. Okay, so let's go back to another problem we know how to do. The Ensemble Kalman filter works pretty well for big problems. So why is that? Well, let's go back to this simple example that I showed you with everybody being ID and Gaussian. And let's just do the ENKF for this problem, okay? So I'm going to take an ensemble size of 20, and I'm going to look at two things. I'm going to look at the mean squared error of the ensemble mean, posterior ensemble mean, so basically my posterior estimate. And I'm going to look at the variance that the ENKF predicts for the posterior. Okay, so this is the mean squared error. Basically, as the ensemble size, as the state dimension gets bigger with a fixed ensemble size, the ENKF is going to the point where it's doing nothing. Okay, so the mean squared error you expect if you just use the prior is 1, or if you just use the observations is 1. So as the dimension gets big, the ENKF is doing nothing, but at the same time, its estimate of the posterior variance is going to 0. Okay, so even though it's really giving you an estimate that's not doing anything, in fact, it's telling you that the estimate is getting better and better. Okay. So in this sense, the ENKF is failing in a very similar way to the particle filter. It's overconfident, and it's not using the observations very well. Okay, so we know why this is happening, because there's sampling error, and when you estimate covariances in the ENKF, those covariances are incorrect. Okay, so the sampling error is order 1 over the square root of n in each element of the estimated covariance matrix. But the problem is those sampling errors are correlated, and so global properties of the matrix are poorly estimated. It has a whole bunch of 0 eigenvalues, for example. Okay, so this is the key thing that you have to do to make the ENKF work in this problem, is you have to do some kind of localization. You have to enforce sparsity on this estimated sample covariance matrix, okay? So the way we do it in atmospheric science is we basically do a pointwise multiplication of the sample covariance by some correlation matrix, assuming that if you go, the covariances for things that are sufficiently separated should go to 0, okay? So when you do this, now you've taken a sample covariance matrix that has it's rank deficient, all sorts of problems, and you've gotten a new estimated covariance matrix that is much nicer, much better behaved. Okay, so there's two differences. There's a difference in how you think of the analysis increment in these two cases. So if you don't do localization, then the analysis increment is just a weighted sum of differences among the members, okay? It lives in the ensemble subspace. But if you do localization, then you basically got this spatially varying linear combination. And you no longer live in the ensemble subspace. Okay, so if you just go back to a simple example, of course it works great. What I'm showing here are results for 3 different localizations. The last one being, if you localize completely, just keep the stuff on the diagonal. So the more you localize in this problem where it really is diagonal, the better it gets, okay? So this all motivates, the main point of the talk is that we have to do, in my view, if we want to do high dimensional particle filtering, we're going to have to think about localization. We're going to have good ways of doing localization. Okay, so the first thing you can do is you can compute these weights locally. So Yohanny asked, how do the weights account for all the observations? Well, in the naive particle filter, the likelihood is based on all the observations, but why not just compute weights based on some local subset, okay? So It's easy to compute local weights, and so now we basically replace this set of weights, 1 per member, with a set of spatially varying weights, 1 per member, okay? So now what can we do with these things? Well, there's kind of an obvious approach. So we've got local weights, and now we're just going to do kind of what the standard particle filter does. We're going to reweight locally. We're going to resample from that local empirical distribution. And we are going to rely on the fact that if we have many members, this is going to converge to Bayes rule, and we're going to be happy. But the problem is that local resampling is random, right? So if you resample here and you resample over here, there's no reason those two samples match up. And so you get problems if you would like your solutions to vary smoothly in space, which usually we do. Okay, so there are ways to deal with this. One option is to kind of do conditional sampling. So you resamples in a location, and then conditional on what you did there, you resample next to it, and so on, okay? There's also some quasi-deterministic techniques that Steve Penny has worked on that seem pretty promising too. So there's kind of a list of some references here that touch on those. Okay, then there's another approach that is really looking at trying to preserve certain the lower moments from this empirical distribution, okay? So the first thing is if you have local weights, then it's easy to do a local estimate of the posterior mean. So you basically just take your particles and you do this pointwise multiplication by the local weights, and now you've got an estimate of the posterior mean. Because if the weights vary smoothly, then we're not going to have any problems. The posterior mean is going to be estimated smoothly in space, okay? So this is going to be a nice thing. One trick that wasn't obvious to those of us who worked on this a long time ago is that you should take a sliding spatial window when you estimate the weights. So you shouldn't just break up the observations into, partition them. For any location, you should use a set of observations, and then the next location should use an overlapping set of observations. Okay, so you can also do, just as you can compute, you can estimate the first moment, the mean, given these weights. You can also estimate covariances given these weights, okay? So you can think about computing a local sample covariance from the empirical distribution, and then trying to somehow update your particles to match those, okay? So there's a really nice paper from, I don't even know how to pronounce these guys' names, Toder and Ahrens, that basically show how to get the first two moments kind of in the framework of an ensemble transform technique, given these local weights, okay? Jonathan Potterjoy's method fits into this a little bit. He's using this local estimate of the mean, and then there's other stuff that I can't really speak to adjust the rest of the distribution given that. Okay, but the thing is that this is not a full solution to the problem, right? Now we're kind of abandoning the original goal, which was to get the full PDF, and now we're just trying to sort of update the first two moments of the distribution. So there are definitely bad things that can happen in that situation. You're not going to capture all possible non-Gaussian behaviors. Okay. So the third approach here is what Walter talked about yesterday, so optimal coupling. So the basic idea here is that instead of trying to directly estimate PDFs or decide how the PDF changes between the prior and the posterior, what I'm going to do is something that seemingly is even harder. I'm going to look for a transformation, a function that maps me from, if I have a variable that has distributed as the prior, I want a transformation that gives me a new variable that's distributed as the posterior, okay? So rather than looking for PDFs, I'm going to look for functions that go between on the state space, okay? So this function is like even more complicated than the PDF itself, at least in principle. Okay, but if you have a discrete random variable, so if I start with a sample from a PDF and I just want to get a new random variable that matches a different sample with different weights. So this is what I have from the particle filter. I start with, I've got particles and I reweight them, okay? So in that context, I really just want a function that maps me between these two empirical distributions. Right, so where am I? Okay, so it turns out you can do this transformation. It's much cheaper, okay? And so this optimal coupling idea comes in that there's a whole bunch of these functions that can go between, that can give you a new variable that's distributed as the posterior. What you want is you want the transformation that sort of has the least expected movement of the particles, okay? So you really want to try and find the one that moves things around the least. And this is going to be useful, you can expect, if you want to preserve spatial continuity. Okay, so once you start thinking in this transform viewpoint, then you can immediately see that you can compute the weights locally. And you can compute these transforms locally. And if the weights vary smoothly, the transforms will vary smoothly. And then you're going to get spatial continuity sort of as a byproduct of this, okay? So it turns out that even though computing this discrete optimal coupling is feasible, it's relatively expensive. It involves a linear programming problem. And so one can look at approximations to that optimal coupling that only preserve the lower moments of the distribution, so the first and second moments. So there's kind of a coming together of this viewpoint and the moment matching one on the previous one. It doesn't matter, I'm almost done. Okay, so this is the summary. So basically, what I tried to show you is that the naive versions of both the particle filter and the Ensemble Kalman filter fail in a similar way. So if you have an ensemble size that's small compared to the number of, to the dimension of the state space and to the number of observations, then what's going to happen is that you're going to get a poor estimate. You're not going to use all the observational information. And you're also going to get the method is going to tell you that your estimate is way, way better than it really is, okay? And then that kills you when you start cycling this. So if you go from that estimate to the next time, now you just compound the amount of underestimation of variance. And so the limit is in the particle filter where you just decide one particle is perfect, okay? So I didn't really show this in detail, but basically there are results that say for any particle filter using sequential importance sampling. So there's a subset of the, I'm done, okay. Within that class of particle filter algorithms, you can show that they all suffer from this this need for exponentially large ensemble sizes in an important class of problems like NWP. So the key here for both these methods is to do localization of some kind. I think this is, in my view, this is like the best idea ever. It makes these things, the algorithms cheaper, it makes them work better, and yeah. So localization is an idea that we should be pushing hard on in the particle filter realm, but there's the difficulty of maintaining spatial continuity, which you sort of get for free by taking linear combinations that vary smoothly in space in the Kalman filter case. So there are lots of options for doing the localization. It's kind of early days just to say which one is going to work out the best. And then you can layer on top of these, as Walter was talking about yesterday, there's a number of other enhancements that can get you sort of increments, beat down this exponentially large ensemble size that you need to get you to the goal of doing particle filtering in these really high dimensional problems. So that's all I have, and thanks for your attention.
Great, thanks very much, Chris.